All right. We've waited like a little bit. So basically I'm just gonna like go over like an intro to the workshop and I'll talk a little bit about Lucas, who's our presenter. And then afterwards I'll just hand it over to Lucas and he can start talking. Okay, cool. So this workshop will be about 3D printing, as most of you probably know. The format will be roughly 20 to 30 minutes of presentation time from Lucas. It's not going to be exactly that, but it'll be somewhere in that range. And then Q&A for the remaining time. If anyone has any questions as the presentation goes along, feel free to post them in the YouTube chat. They'll be answered after each slide if we're able to do that. And then at the end, we'll have some more time for dedicated questions. I'll briefly introduce like the team that's speaking, and then we'll get into the presentation. So the team we have presenting today is FTC Team 16461 Infinite Turtles from Matthews, North Carolina. Last year, they were second place in Spire in their division at Worlds, and the year before that, they won Innovate at Worlds and were finalists in their division. 16461 always has like really well manufactured parts, and we're really excited to have them presenting 3D printing to us. So without further ado, I'll hand it over to Lucas.
Okay. What's up, everyone? So, as Cooper said, I'm going to be talking about 3D printing for FTC. So, let's just get into it. And the first question I want to answer is, what is 3D printing? Which is it's just an additive manufacturing technique where you melt plastic and you create custom parts layer by layer. So you stack them almost like a sandwich, basically. And as for applications, you can use 3D printing for a lot of different things. And a general rule of thumb is that you can use it to print basically anything, as long as it's, strong enough and isn't like bearing a ton of load and it won't, break under the loads that we typically see in FTC. So some places where it's used are gears as well as pulleys to power wheels, claws and arms. So on the left is an example from this year. That's an open source design created by a CAD team. And this claw is virtually fully 3D printed. And then on the right, that is an intake from our robot in Freight Frenzy. And as you can see, it's almost entirely 3D printed. So the gears on the right or on the left, sorry, as well as the surgical tubing mounts, as well as the spacers. And then finally, one of my favorite uses for 3D printing is aesthetics. So these are both examples that my team has used. On the left are sponsorship badges that we used on our state spot in Freight Frenzy. And then on the right is our world spot, where we use 3D printing as a stack between our metal plates to create this kind of turtle shell effect. And also, I just want to touch on the advantages of 3D printing. The first one and the main one is rapid prototyping, as well as having quick turnaround times. The second one is being able to create precise details. And the next one would be having more mounting options versus commercial parts. And the reason I say this is because with 3D printing, you can really customize where you're mounting certain things. Whereas with commercial or off the shelf parts, you're limited to the specific hole pattern of the vendor you're buying parts from. And finally, it also gives you good design experience as well as, learning CAD skills. But I also want
All
to
right.
touch on, oh, go ahead.
Oh yeah, really quickly, Lucas. Coda in chat asked a question. They said when 3D printing something with threads, will they go away over time?
Yeah, so I'll actually talk about that a little bit or in a bit, but in general for threads, if you're threading directly into a 3D printed part, it's a good idea not to, take out that screw and put it in like over and over again, because over time, like it will wear out compared to metal threads, but there are ways to like get around that, and I'll make sure to address that in a bit. So as for the disadvantages of 3D printing, um, prints do still take a long time, and you'll probably be confused because in the slide previously, I just said that there's a quick turnaround time and that the prototyping is rapid. But I think there's a distinction to be drawn here. in that like the prints do take a long time, but in the grand scheme of things, if you're considering, how long it would take to order from a vendor, get those parts shipped out and delivered to you, 3D printing would still win out in terms of like just against COTS parts or off the shelf parts. The second disadvantage is that 3D prints are less strong than metal parts. There are ways to increase the strength of 3D printed parts, but in general, plastic is not going to be as strong as metal. So we typically try to avoid using 3D prints in places where a robot would be stressed. Next is that there's somewhat of a learning curve to 3D printing. And while with newer printers with better technology are coming out that lower this learning curve, there is still very much a component of knowing what you're doing, which makes it easier to 3D print and 3D print well and consistently. And then lastly is that 3D printing can be expensive because you obviously have to purchase printers as well as filament, and then that adds up a lot over time. But as I said, there are newer 3D printers coming out that really lower the cost of entry into 3D printing. So whereas maybe like a decade ago, it might cost $1,000 to $2,000 to get into 3D printing, now you can get into 3D printing at a very low cost while achieving the same, if not better, results. With that being said, we're going to talk a little bit about printer choice. And so up on the screen, I have three different printers, and they range from, budget printers to mid-tier to high-end. And so on the left would be the Ender 3 series. And even if you haven't really, like learned that much about 3D printing, a lot of people have heard about the Ender 3. And it's basically the go-to budget machine. It's just overall pretty solid. It's really cheap and you can upgrade it to perform really well. But as for the cons, it is somewhat unreliable out of the box. And so, over time, you may want to upgrade it with, aftermarket parts to make it more reliable, more consistent. In the middle is the Bamboo Lab P1P. And Bamboo Lab is a relatively new company to the 3D printing scene, but they've been making a lot of, big waves because their printers are not only priced very well for the features that they deliver, but they're also very receptive to community feedback. And so this printer, the best thing about it is that it is really, really fast and it is really, really reliable. The biggest con to my knowledge is that a lot of the replacement parts are proprietary from Bamboo Lab. And while I think that these parts are well priced, there's definitely something to be said that the prices of these parts could increase in the future, which may not be a good thing. And then finally is the Prusa Mark IV, which I have on the very right. Prusa is a brand that's been in 3D printing for a very long time. And the hallmarks of their printers are generally that they make very, very reliable printers that you can use for a very long time and have very consistent results with. And while their printers are priced quite a bit above, like more mid-tier and budget printers, they are incredibly reliable and they will serve you for a very long time. And obviously, there are a lot more printers than just the ones listed right here, but these are some of my personal favorites for the price points that they're priced at. And so, it's all if you're planning on getting, different printers, it's always good to do your own research. But I think Creality, Bamboo Lab, and Prusa are definitely vendors that make great printers, and I would definitely recommend to anyone. Now I wanted to talk a little bit about filament, which is what you're actually is the plastic that you're actually using to print. And these are the four main types of filament that we typically see in FTC. There are a lot of different filaments that aren't listed here, and you can feel free to experiment, but these are the four that I would recommend specifically for FTC. Now, the first one is PLA. PLA is, just like a really good all-around filament. It's priced really well, and it has great strength properties. It's not like crazy strong or anything like that, but for most FTC use cases, it should be good enough. And then for cons, its PLA can be quite brittle, and it's also not very resistant to UV rays. And there's also a distinction between strength and brittleness because, like, while PLA is fairly strong for FTC use cases, what I mean by brittle is that when it is stressed, it tends to crack rather than bend. And then the other use case, or sorry, the other con of UV resistance, um, typically this won't really manifest itself in FTC, but it might not be a great idea to leave your robot in the car in the sun for an extended period of time, or the printed parts will start to degrade. As for good brands for PLA, um, these are some of my personal favorites that I've worked with: eSun, Polymaker, Hatchbox, and Overture. Our team personally uses eSun, but for PLA, I think really any filament that you can find on Amazon with really good reviews should do the job. The next filament is ABS, and ABS is the strongest filament out of all the ones I have on this page, and that's really why a lot of people use it. But as for the cons, ABS is pretty tricky to print with, and there are also some safety hazards to printing with ABS, those being styrene fumes. So it's generally advised that you print ABS with an enclosed printer with a filter and in a well-ventilated environment, because these fumes are known to cause headaches, as well as some other negative side effects. Um, as for good brands, I really like eSun's PLA Plus or ABS Plus because it's a lot easier with than normal ABS. And then KVP and Polymaker have really good normal ABS blends as well as really good colors. Next up is PETG. And PETG, I think of almost as like a better, or if you should use PETG when you need extra strength in your parts, but you don't want to deal with like the extra trickiness that comes with printing with ABS. And so PETG has great durability and it's really impact resistant as compared to PLA, which can crack and is like pretty brittle when it's subjected to stresses. But as for the cons, I would say it's a lot more tricky to print with than PLA, and also it tends to absorb moisture at a quicker rate than PLA does. But as for the good brands, I think that all the good PLA brands also carry over to PETG. And then finally, I also have kind of a specialty filament up here, which is TPU. And the main point of TPU is that it's flexible, and so it's and that that quality also makes it pretty hard to print with because the extruder gears can sometimes slip, especially on TPU blends that are more rubberized, I guess you could say. It also absorbs moisture fairly quickly, but sometimes flexibility is something that you want to have in your prints, and so that's where TPU comes in. As for good brands, I personally haven't worked with a lot of TPU, but I have heard a lot of good things about NinjaFlex, and in particular, they make a really great blend of extremely flexible TPU. And so I think with TPU, one of the main things you want to pay attention to is the durometer of the TPU, which is just like a measurement of how bendable or malleable it is. And so you just want to pay attention to that when considering like what you're using it for in your use case. Now we're going to talk about post-processing and add-ons, which I'll also address the question that was asked earlier about 3D printed threads with heat set inserts. So heat set inserts are basically metal inserts that are made of brass that you use a soldering iron to press into your 3D prints. So you're basically printing a undersized hole in your prints and then melting around that hole to push the inserts in. And these are used to add threads to your 3D printed parts, so that your screws don't round out your mounting holes. And the reason I like heat set inserts is that they're really easy to design with and as well as use. But as for alternatives, there are also self-tapping screws as well as just putting up designing a spot where you can put like go build a nuts or lock nuts inside of. And so there are really a lot of ways to get around having to use 3D printed threads. Well, so those are all great options, but personally, I love to use heat set inserts. Next up, I want to talk about annealing. So annealing is something we do to increase the part strength of 3D printed parts, and it typically increases the strength the most in the Z axis. So if you think about how 3D prints are made, they stack up one by one. But those individual layer lines create places where 3D prints are inherently weak. Because if you think about like a solid piece of plastic, there are no lines where it can like crack along. But with 3D prints, those layer lines are inherently weak. So what we do with annealing is we put the print in an oven or a heat source to melt those layer lines down and effectively create one solid part. Next up is vapor smoothing and epoxy coating. I'm going to talk about these kind of together because they accomplish the same effect but with different means. And that effect is, to smooth out the surface of your 3D prints and make those, layer lines not as visible. Vapor smoothing does this by using chemical reaction to actually melt down the outer surface of the prints, whereas epoxy coating, you're actually brushing something on. And typically we don't see this a lot in FTC, but if you want like low friction parts or you just want to add a little bit of extra strength, that's the way to go. Okay. Next up, I'm gonna talk about how to design for 3D printing, and I'm actually gonna walk through a couple of examples of parts that our team has printed before, and how those parts were specifically designed to be 3D printed well. So the first part of designing is that you need or the first part of printing is that you need CAD files of your parts to be printed, and you can use any software to design these parts. Our team personally uses Onshape, and I know a lot of teams use Fusion 360, but I would personally recommend Onshape if you don't already have like experience with other CAD software because it's really easy to pick up. It's browser based and it has a lot of support. Um, and so one of the biggest general rules to keep in mind for 3D printed parts is that you shouldn't have overhangs over 45 degrees. So if you look at the graphic in the bottom left corner, the first two graphs show, or the first two pictures show overhangs of less than 45 degrees and equal to 45 degrees, whereas this picture on the right shows an overhang of over 45 degrees. And the reason we don't want to use, or we try to stay away from overhangs over 45 degrees is because if you think about the way 3D printers work, they work by stacking layers on top of each other. And so if you had a perfect 90-degree overhang, you would basically be printing in midair, which, doesn't work. As the overhang angle goes closer to 45, it'll be better, but it'll still require the use of supports because, one thing that 3D printers are limited a lot by is, how fast they can cool the plastic coming out. So if it can't cool the overhang fast enough, since it's not being supported by anything other than the previous layer, then it can result in some, pretty bad print failures or just, not making the part the way you wanted it to be made. And then the other thing I also wanted to touch on is tolerances. Because no 3D printer is really perfect. And 3D printers are not as accurate as things like CNCs. They can't hold tolerances as well. And so if you have a 4 millimeter screw hole in your CAD, it could end up bigger and smaller once you actually print it. But one thing that I want to mention here is that while 3D printers don't hold tolerances well necessarily, they do hold tolerances pretty consistently. So if your 4 millimeter hole is consistently it'll be consistently 3.8 millimeters or consistently consistently smaller or consistently larger than that hole size. And so you can either adjust that in CAD or you can adjust that in your slicer, but it won't be like you have one hole that's bigger and then one hole that's smaller for some reason. And so this is something I wanted to mention about, designing things to be printed easily. So on the left is a part that doesn't have or a lot of contact to the build plate of the 3D printer, which is this bottom checkered surface. And the reason that's bad is because we typically want parts to have good adhesion to the print bed. Otherwise, they can fall off, warp off, and fail. Whereas on the right, this part has a lot of contact to the print surface, so it's less likely, to warp up and fail, even though it is a bigger part. And now the second thing I wanted to talk about here is this two-piece part. This part was originally one piece, but as you can see, it's really it would have been really difficult to find a flat surface for this part that doesn't use supports. And so what we actually decided to do was to split this part in two, with the green part being one piece and the white part being the other piece. And so this allowed us to have two parts that were really easy to print separately, and that we could use screws to join them together afterwards. And now this is one of my favorite parts that I've designed. And so this was actually a hard stop for our arm this season. And so when our arm would come down, it would rest on top of this. And it also was a mounting point for our color sensors, which is this excess piece that you see here. And so the biggest takeaway from this part is designing for overhangs. So there are two places where that really takes place, and that's this excess part right here, as well as the part at the top. So in both of these cases, the overhang is 45 degrees or less. And if you look at the right here, I drew a red line to show where I could have stopped this part had I not been thinking about designing for 3D printing explicitly. But because that was kept in mind, I actually decided to increase the angle of this bottom part here to be exactly 45 degrees so that it could be printed without supports. Now we're going to talk a little bit about slicer settings. And just to answer, what a slicer actually is, a slicer is the step between CAD and actually printing the object. So after you have your CAD file, you'll put it into a slicing software, and basically it does exactly what the name implies. It slices your model into the individual layers that your printer actually reads, and that's called G-code. And so in the slicer, there are a couple different settings you can configure for your part, and this will change the properties once your printed part is finished. So the first one I wanted to mention is wall count. And if you look to this picture on the right here, that's that outer boundary around the parts. And it's just how many, passes of the around the perimeter of the part that the printer is going to do. I would recommend at minimum to always use 2 walls. But if you want your part to be strong, you'd probably want to use 3 to 4 or maybe 5. The second thing is infill, which is what this picture on the right is really trying to highlight. And so there are a lot of different infill patterns that you can use. And there's maybe 15 to 20 that are baked into slicers, but I would really only recommend 2 of them, those being cubic and gyroid. And the reason I picked those specifically is because those are 3D infill patterns, which means that rather than having the same cross section as you move layer to layer, the cross section changes, which means that your strength in the z-axis is less compromised than if you use something like a grid infill pattern or like a triangle infill pattern. As for infill percentage, that describes how densely you want the infill. And so the greater your infill percentage is, the more solid your part will be. Uh, and my general rules of thumb for that are, if a part is purely for aesthetics, I'll use between 5 and 10%. If the part is semi-functional but isn't any under any like heavy amount of load, I'll use 20 to 30%. And then if it's actually under like a decent or significant amount of load, I'll go anywhere from 50 to 100%. Um, and another reason behind why we use infill is because very rarely will you need your print to be 100% infill, or in other words, a solid piece of plastic, just because the load cases in FTC don't really necessitate that. And, another thing about using 100% infill is that it can be more costly because you're using more filament to fill the gaps in between your prints. The next thing would be speed, and this is largely printer dependent. So ender printers, I would say, like, don't run them above 80 millimeters per second. Otherwise, you'll start getting weird issues. It'll start under extruding, etc. But with printers like Bamboo Labs, those typically run at speeds of 200 to 300 millimeters per second. And so, as you can imagine, those printers will be a lot faster than some of the more budget printers, but that doesn't mean that you can't upgrade budget printers to run faster. The next thing would be temperature and cooling, and this is very, very filament dependent. So just to give an example, PLA filament typically runs at 215 degrees Celsius for the hot end and 65 degrees Celsius for the bed. And you typically want to use as much cooling as possible for PLA. But whereas with a filament like ABS, your hot end runs around 245 degrees Celsius and your bed runs at around 110 degrees Celsius. And you actually want to use around only 30 to 40% cooling for ABS. And finally, is your choice of slicer software. And I don't think this matters too much, so I just gave two broad suggestions. Ultimaker Cura is what I would suggest for beginners, and Prusa Slicer is the slicer that I would suggest for more advanced users. Functionally, these aren't too different, but Prusa Slicer gives you a lot more values to adjust of your printer. So if you want to do something, really specific or do something interesting with your prints, Prusa Slicer might better enable that than Cura does. But I think for the vast majority of teams, Cura is a perfectly fine software. And I actually use it myself sometimes because they do a really good job of actually implementing features that people will use. The next thing I want to talk about is a little bit about print troubleshooting. And there are a lot of things that can go wrong with 3D prints, but I think the biggest thing that I see a lot of teams asking about is print bed adhesion. So what that means is how well your print sticks to the build surface. And that's really important because we want the print to stay, obviously. Otherwise, our print moves won't be accurate. And so if your print isn't sticking to your bed, it could be a couple things. The first thing could just be that you're printing too high. And in that case, you want to adjust the height of your prints or the height of your nozzle down closer to the bed. The second thing could be that your print surface is dirty. And I actually don't really like the advice on this slide. What I would recommend is for if your print bed is dirty is taking a little bit of dish soap, scrubbing your bed with dish soap with a sponge, and then drying it off with a microfiber cloth. I wouldn't really recommend paper towel because that can leave residue on your bed, which might actually make adhesion worse. The next thing would be just applying a light layer of glue stick. I actually use glue stick on the vast majority of the prints I do, just because it's kind of a cheat code to creating bed adhesion. But one note is that if you do use glue stick, I would recommend from time to time, wiping off that glue stick with dish soap and then reapplying. And that's for a couple reasons. First of all, the print bed just tends to get nasty over time because like debris just sticks to the glue. And the second reason would be that, if you print like in the center of your bed exclusively, then that glue stick will start to go away and you want to reapply to keep it, fresh. And these last 2 points here, or yeah, these next 2 points here, are just other alternatives for creating adhesives. Hairspray, I've heard works fairly well. And then also just like a glue water mix that you spray on can help create like a nice even layer. And the final point here is to level your bed. Um, it's kind of a joke, level your bed in that the vast majority of teams that have difficulties with 3D printing, all of it can be traced back to the fact that their bed isn't level. Because if your bed isn't level, and what that means is that all parts of your bed are flat in relation to each other, a lot of things can go wrong at the very start of your print. And so your print never even reaches the final stages where like other issues start to manifest. Now I want to talk a little bit about prints sticking too much. And so typically this doesn't happen unless you're printing too close to the bed because the prints should release once your plate cools down. But in the case that, this does happen, you want to adjust your Z height up. Another tip that I've personally used is spraying water around the edges of 3D prints or using aerosol upside down on the edges of 3D prints, which will just help like rapidly cool the air around where your print is. And then using the water will also enable like capillary forces to pull the print off of the bed. But this next tip is actually my favorite, which is using like a bed scraper or like a thin object. I use a ruler and just tapping it lightly with a mallet or a hammer. And I found that this works almost 99% of the time. And it works really well. And then these last 2 points is, just being patient and waiting for your bed to cool because prints are not really designed to be released when your bed is heated. And so waiting for the bed to cool or just putting the bed in like your fridge or your freezer can help just take the prints off. And now I just wanted to talk a little bit about bed leveling, which was mentioned on the previous slide. And so if your print bed is too high, then the nozzle will, or the plastic coming out of the nozzle will kind of just be dragged around the bed. It won't really stick to the bed where it was meant to be put down. Whereas if the print bed is too low, then the tip of your nozzle will dig into the filament when it's extruded, and this will kind of create like ridges in your print, which are fairly noticeable. But if your bed leveling and adjustment is just right, then the tip is pressing into the filament slightly, but it should stick to the bed very well. And there shouldn't be any noticeable gaps in between the lines of your print. And so what this kind of looks like is this. So on the left, the print nozzle is too high. And so you can see that there are there are gaps in between each of the lines. And it's not really like staying flush to this wall, these perimeters. And then on the right, you can see when the nozzle is too low, that you're not really getting a lot of extrusion. You're seeing those ridges. And because the nozzle is pressing so far into the filament doesn't really even come out very well. Whereas in the middle here, when your bed level is set correctly, you'll see that there are really like no gaps in the filament and that it's all very flat. So that basically wraps up the presentation. And I just briefly wanted to talk about some resources for 3D printing. The first one would be FTC Docs. And this is the official first documentation. And it has a really long section about 3D printing which our team contributed a majority to, a majority of. The next one on here is All 3DP, which collects filament data as well as gives printer reviews. So if you're looking to buy a new printer, I would definitely recommend looking at some of their reviews. Next is CNC Kitchen. This is a guy on YouTube who does a lot of scientific and strength testing videos on filaments as well as print settings. And a lot of the data he has is really good. And I would definitely recommend checking him out if you're considering doing something like more interesting with your 3D prints. Um, the FTC Discord is another great resource. And specifically, the manufacturing channel in the FTC Discord is really helpful. It's a lot of more knowledgeable people about 3D printing in that channel that will help people troubleshoot their issues. I personally, help a lot of teams in that channel. So you can ping me if you're ever there. And I also wanted to touch on our own team's resource, which is Core FTC. Um, Core FTC originally, or sorry, the content on Core FTC was merged into FTC Docs, and so a lot of the info on there came from Core FTC. And this was originally a 3D printing guide, but over the next few months, we're going to be shifting it to some more technical 3D printing advice, as well as surprise that will be revealed at some point. Um, and lastly, this is just my contact information. On Discord, I regularly check that. So if you message me any questions on there, I'll answer. This is my email. And if you want to reference any information in this presentation or click on any of the hyperlinks here, this is the URL for this presentation. And I also just take any questions now.
Okay. So Ivan asked in chat, what are the steps to troubleshooting a failed print? Do you do redesigning first or try to find issues with the printer?
Yeah. So, yeah, that's a really good question. For troubleshooting, I think most of the times it's the printer, not the part. There are some instances where it'll be the part, but in those instances, it'll be fairly obvious. So for example, if you're trying to print in midair, the printer obviously isn't going to be able to do that. But for troubleshooting, generally there isn't like a roadmap as to how you go about that. You usually want to identify what the failure case looks like, and then based on the failure case, then you can determine a list of things that might be causing that, and then you can go through that one by one. And so that's something that will come with experience, but also you can also just use, the power of Google. So if you notice that, for example, your print is under extruding, which basically just means it's not putting out as much material as it should, you can just Google reasons 3D printer might be under extruding. And there are websites that will list like every possible reason as for why. And then you can just check to make sure it's not, those reasons.
Okay. So Hudson in chat asked, what printer do you have?
I have a VZ bot, and I think Hudson knows that.
Okay. A couple of other questions because you have some more time. So if anyone has any other questions, you can just put them in chat. But there are a couple of like frequently asked questions that I've compiled, and I'll just ask them really quick. So first off, if somebody has never 3D printed in their life before and has like $1,000 budget, what do you think they should get? And how about like $250?
Okay, so I'm gonna go backwards here. So for $1,000, I would get, honestly, I would get the Bamboo Lab P1P over the Prusa Mark IV. And the reason I'm saying that is because while I think Prusa printers are very reliable, the Bamboo Lab is honestly just a much better bang for your buck. But I think the Prusa is also a really good option And if you're already like invested into the Prusa ecosystem, the Prusa Mark IV might be worth it. As for $250, um, I think getting an upgraded version of the original Ender 3, so either the Ender 3 Pro, Ender 3 V2, or a similar Ender clone can be good. And I think specifically at the price point of $250, um, I would recommend getting an Ender clone because those machines typically have a lot more features than the original Ender series does. And while they're less tested than the original Ender series are, they pack a lot of features. And for some of the more notable Ender 3 clones, they actually have a lot of people that use them and they have an established knowledge base as well as like support team.
Okay. So I know you recommended the Bamboo Lab P1P. I was curious on what your opinions are on the P1S, which is, I guess, the new Bamboo.
Yeah. So the P1S is basically the P1P, but with an enclosure. And there are some other minor tweaks, but those are more quality of life than functional. So the main thing you're going to be gaining out of the P1S is an enclosure. And so generally in FTC, you won't need an enclosure when 3D printing. An enclosure is generally used for engineering grade filaments or specifically ABS because those require having a heated chamber to be printed well. But in FTC, I really think for teams starting out that PLA or PETG is definitely the way to go, and neither of those options require or even should be using a heated chamber.
Another question is, because an enclosure is like used to print some of the, I guess, more like exotic filaments, what are your opinions on like some filaments that are like gaining traction now? They're maybe more popular and maybe less used. But stuff like, I don't know, like carbon fiber or like onyx.
Yeah. So, my opinion on engineering grade filaments is that for the most part, they're not necessary, but they definitely do help when you need them. So the example that comes to my mind is two seasons or yeah, in Freight Frenzy, our team designed a mechanism called locking mecanum, which basically pushes up against the mecanum rollers of the wheel and it stops them from moving, which allows us to gain traction. And so one issue we're having when using PLA in that use case is that it would get so hot because of the friction inside of the wheel that the PLA would straight up just melt. And so we used nylon Kevlar, I believe it was, for the linkages inside of the wheel, and that worked out really well for us. But generally, for the majority of parts, particularly the ones I listed at the start, you won't really need exotic filaments. But I do know that they're being used more by teams, and I think that they're becoming more accessible. And specifically, blends of like more typical filaments with carbon fiber or exotic filaments are much more affordable and usable than they were a couple years ago. And so, off the top of my head, just like PLA carbon fiber, ABS carbon fiber, like glass fiber infused filaments, and stuff like that, is a lot easier to use now.
Another question is, um, a lot of printers have like the option to be pre-assembled or like bought as an entire printer. Like I know the Prusa MK3S Plus has that option. Do you think that teams starting out should buy kits pre-assembled or to be built?
Yeah. So I know that Prusa does this specifically. I think that there are merits to going both ways. So if you're getting a kit, or if you're getting a printer kit built, um, typically it will be cheaper. And another thing that I think isn't really mentioned is that building a printer can actually give you a lot of experience in just like the mechanical aspects of FTC. So I actually built a Prusa Mark 3S Plus around 2-ish years ago. And honestly, it was a very fun experience because Prusa does such a good job of documenting um those instructions. They have like their own like forum, I guess, for just like people building the printers. So if there's something that even the instruction manual misses, which is very uncommon, it will almost always be answered by the community. Um, and it's just like a very well documented process. But as for going pre-assembled, I also think that there are merits to that, whereas you don't have to worry about assembling something wrong, or if you're just not confident in assembling the printer, getting uh pre-assembled would be a better option. Um, but getting a pre-assembled printer does typically cost more than a kit built. So for Prusa specifically, the price I have here is for the pre-assembled version, whereas the kit built version, I I don't have the number on the top of my off the top of my head, but I think it's 899 or a little bit more than that.
Okay. Another so I think the Prusa MK3S Plus pre-assembled is like 900 to 1,000. I think the pre-assembled is like 650 or something. I mean, not pre-assembled is like pre 650 or something like that. But another question is, I know a lot of people like me when I first bought my first 3D printer um have like a big problem with the time to like build a kit. How long did it take you to build like your 3D printer, and like um do you think that was like a big challenge?
Yeah. So I've actually built two printers. One of them was the Prusa Mark III that I mentioned, and then the other one was um, a Voron, which is a DIY printer. So the Prusa Mark III, I believe, took around 4 to 6 days to build. I don't remember the exact number, but I think that number can definitely be cut down upon because that was just me building the printer. But if you have a whole team assembling it in sections, that you can definitely get that number down. Um, and another thing is those 4 to 5 days was typically me assembling the printer after school for 3 to 4 hours, I would say. And then the Voron, it took me around, I want to say, 8 or 10 days to build, and that printer was a little bit more involved. Um, but I don't think that building the Prusa was a particularly difficult task. Um, there were some sections where there was like a little bit of a trick to getting parts to fit together. Um, and while that wasn't like explicitly mentioned in the instructions, there is like a forum of people who are building a Prusa, and under the forum there are like comments for how to do specific things because there are a lot of people that have built these printers and they have figured out like where sometimes the instruction manual is a little bit lacking, and then they've created their like own solutions to those problems.
Okay. Another question by Hudson in chat is, do you think there's a place for SLS printing in FTC?
Um, yes. Yes. But for the vast majority of teams, they will not need an SLS part. And for people that don't know what SLS is, it's just so it stands for selective laser sintering. And it's typically used to selectively laser sinter out metal parts. So it is a form of 3D printing, but you're printing with metal, which I don't think the vast majority of teams need, but it does have its use cases in FTC.
I guess adding on to Hudson's question about like different types of printers that aren't like FDM, what are
Mhm.
your opinions on like resin printers, and do you think that like they're better or worse than like I don't know, FDM printer for like
Yeah.
FTC?
So for resin specifically, um, I honestly was considering getting a resin printer for personal use. but I do think that for FTC specifically, FDM is a better choice. And the reason I think that is because resin is typically used to get parts that are very, very detailed. And so, the biggest example of that is like people who buy resin printers typically use it to make things like minifigures for board games. And so like that's the level of detail that they can achieve. But for FTC, a lot of the parts we're printing aren't that detailed. They're more macro scale and we need functionality over details. And so like oh, and the other thing is that resin parts typically tend to be less strong than FDM parts, just because of the way resin printing works. And while there are like high strength resins, I think that FDM printers just win out overall.
Okay. Another question is, I mean, I guess it's not really a question, but like, can you tell us a little bit about like multicolor printing? Like, do you recommend getting a specific printer for that, or do you recommend just like stopping the print, like changing the color and like restarting it?
Yeah. So this picture I have on the left right here is an example of multicolored printing. And this was done by stopping the print, changing the colors, etc. Um, I definitely think that's a viable option if you have the time. But a lot of the times it can be really tedious, especially if you're applying multicolors over several layers. This multicolor print was applied only on one layer, I believe. And so for a specific printer, I would recommend that would be any Bamboo Lab printer with their AMS add-on, which is their system. I think I don't remember the acronym, but basically, each AMS unit allows you to print with 4 different filaments, and it's you can like link together multiple AMSs up to you can link up 4 AMSs for a potential of up to 16 different filaments. Um, Another option I would consider is maybe going the open source route. So there are 2 projects that are very like fairly similar. Those being the Voron Enraged Rabbit Carrot Feeder is the name, and the Annex Trad Rack. Those are both multi-material systems that are open source that you can build.
Okay. Um, I guess another question is because a lot of the people who are like getting 3D printers for FTC, a big concern for them is just like rapid prototyping, like printing stuff really fast. Because a lot of the teams that like use 3D printers have like heavily 3D printed parts. Like a lot of their parts are 3D printed. They have like a bunch of parts on their robot. They're all use 3D printing, and for some of them, getting all those parts printed in time might be a challenge. So if that's a concern for people, do you recommend getting like multiple G printers, like multiple Ender 3s, or like a higher end printer like I don't know, like a Bamboo X1 or like P1P?
Yeah. So as a team that does a lot of 3D printing, um, our uh our main printer is a Bamboo Lab X1 Carbon, and I think it does a very, very good job for us. Um, However, I do think that in the end, more printers will win out over more expensive printers. So while I wouldn't necessarily recommend getting multiple enders just because enders might take more maintenance, I would definitely get maybe like 2 Bamboo Lab P1Ps or maybe like 3 Prusa Minis or like 5 Ender clones or something rather than a Bamboo Lab X1 Carbon. The reason we went for an X1 Carbon specifically is our team does like to experiment with like certain engineering grade filaments, as I mentioned before. And also uh, the way our team does our design process means that since we have to wait for like our plates and other stuff to be shipped anyway, we do all of our printing while our the rest of our stuff is getting shipped. Um and so we don't really have have to print on a time crunch, if that makes sense.
Okay. To add on to a little bit about what you said, so you talked a lot about the X1C, um,
Mhm.
which is another bamboo printer. It's a bit more expensive. I think it's like 1,300. You can correct me if I'm wrong. Um, but what's the difference between the X1C and P1P, and like what are the benefits and cons of each of them? Because I know
Yeah,
both of them are like really popular.
yeah. So the like chain from like worst to best, I guess, would be the P1P, then the P1S, then the X1C. Another thing is the X1 Carbon is not being sold anymore. It's just called the Bambu Lab X1 now. Um, the Carbon Edition was like something they did, or something that they were selling up to like a month or two ago. But essentially, or sorry, the X1 is not being sold anymore. The X1 Carbon is still being sold. Um, but essentially, the main difference between the P1P and the P1S is the addition of that enclosure. And then the main difference from the P1S to the X1 Carbon is, I believe, a hardened extruder, which lets you really push the limit with like engineering grade filaments. It adds LiDAR, which basically scans at the before the start of your print, and it does like some calibration with that. I forgot what it does specifically, but it does help somewhat. There are also it also comes with a colored touchscreen versus this like cheaper LCD display, which can be helpful. And then there are also some minor quality of life benefits that I believe it comes with. I don't know those off the top of my head, but I do know that they exist.
Okay. Well, it's about 7 o'clock, but I guess before then, I guess one other question is, so you talked a little bit about printing while parts are shipping. What's a recommendation for people who maybe are like custom manufacturing parts in-house or something like that? How do you recommend they get all the parts printed in time? Do you recommend they print it like a couple days or so before the building process starts, or do you recommend they print parts as they CAD them? And in addition to that, like what do you think about like 3D printing for prototyping, and how do you think you people should be able to speed that up?
Yeah. So um I think as for the issue of like getting prints done in time, um if you CAD a part and you know you're not going to change it, it's no harm really in just printing it out because you're eventually going to use it at some point. Um, and so that's one way to go about things. And then but if you know you are probably going to end up changing a part or just like the way it looks, I would recommend just like once you're done with your CAD, like you're fully done and everything, just print everything out in batches, before you assemble.
Is you order a bunch of parts like before you build. My question was, you order a bunch of parts while like you print a bunch of parts while you're ordering like parts to be manufactured. My question was, how about when you're just trying to print um oh, okay. I saw something went wrong with the stream. So I got a little distracted. But how do you deal with like printing if you have to print it like really fast to like prototype something or to quickly put on an iteration? Do you have any tips for like making that process really fast? Like should we use like a faster print speed or like lower filament? Like do you have any tips for that?
Yeah, for sure. So there are a lot of things that go into making 3D prints faster. Um, but I think in general, one would be using larger layer heights. And if you have the ability to use a larger nozzle size, those both of those things will cut down drastically on time because if you use a larger layer height, for example, if you use 0.3 millimeter layers versus zero point 0.2, um, you can reduce the amount of layers that you have by like 30%, which is a huge time saving. And if you use a larger nozzle size, that means that your walls can be thicker and the line width of your prints can be thicker. And so that allows you to use like less walls, which also speeds up the process a lot. So there's been a lot of debate in the community because the standard nozzle size that most people use is a zero point 0.4 millimeter nozzle. But in like the past year or so, a lot of people have been switching to using 0.6 millimeter nozzles just because you don't see a huge drop off in quality while still maintain while giving you a pretty significant increase in speed. And I think that there is a huge merit to using 0.6 millimeter nozzles in FTC specifically, because we're not printing extremely detailed parts. With zero point 0.4 millimeter nozzles, you do see like an increase in details with for really fine details. But with zero point 0.6, I think like the speed increase is so good that it like almost puts zero point 0.4 millimeter nozzles out of the question. Another tip I have for getting prints done quickly just for prototyping and testing would be to one, remove material. So any material that isn't necessary, you should just take out, whether that means making your part thinner, just like if it's like a solid piece, maybe just like taking out a section in the middle if you don't need it. Because at the end of the day, if these parts are for prototyping only, you don't need them to hold up over the course of a season. You probably only need them for like a few minutes or like a few hours at most, and then you're going to create a final version of your part that actually has the attributes that you want. Another tip I have will just be to decrease the amount of infill, so maybe to like 10 or 15%, and then using less walls, so maybe instead of like 3 or 4 walls, using only 2. And obviously this is going to depend like on the part you are prototyping, because like like stresses and stuff like that. But just reducing the amount of material you have to put out is another big thing.